Hello everyone. For this little physics video, we're going to cover some basics about waves in the physics class, as well as get into harmonic waves and tension force for an object that has a harmonic wave going back and forth through it. Now, some basics about waves is there are two main types of waves. First is a mechanical wave, and a mechanical wave, that energy can only transfer in that wave if that wave is moving through a physical medium. Mechanical waves can be broken up into longitudinal waves and transverse waves. For a longitudinal wave, if the energy is moving left and right, then the actual medium, the physical material, is also moving back and forth, left and right, as the energy is moving through it. An example of that is sound. Sound is a longitudinal mechanical wave. It can only propagate by physical, actual gas molecules crashing into each other and then reaching our eardrums, or reaching through liquid material or going through solid material. That's how sound propagates. Now, for transverse waves, essentially if the energy is moving left and right, it's making the medium or the material appear to be moving up and down. That's more obvious in ocean waves, whereas the ocean wave energy is moving out from some point, it's making the actual water move up and down. So that would be a type of a transverse mechanical wave. Of the two major types of waves, the second type is electromagnetic waves. Electromagnetic waves do not need a physical material to propagate through space. Electromagnetic waves are light. What we have here is our magnetic plane oscillating in one direction, and we have our electric field plane oscillating in another direction. These two fields can be assumed to be at really any angle from each other, but the easiest way to calculate things is making it so that the electric field is along, say, one plane, and the magnetic field is at an orthogonal plane. And then these two are rotating together as the wave is propagating in some direction with some velocity v. Well, here's how waves can interact with material. Waves can undergo reflection, where as that wave approaches some reflective surface, the angle that that wave reaches a point is the same angle that it reflects away from that point. Now, there's also refraction. That's when a ray of light is traveling through one type of medium and then it refracts into another type of medium. For example, a ray of light traveling through air and then hitting the boundary between air and water and changing its direct angle slightly as it's now traveling through water. In this case, what we care about is our angle of incidence, theta I, and our angle of refraction, theta r. And whatever our boundary is, we want the perpendicular axis to that boundary. And then what we want is the angle between our perpendicular axis and our ray of light. That will be theta I, the incident angle, and theta r, the refracted angle. Those two angles are rarely equal to each other. Now, Another way that waves of light can interact with material is through diffraction. That's where you have an opening or multiple openings in some screen, and then some wave of light that's oriented in some way approaches the opening at the same time across all points of that opening. And then it causes that wave to start propagating in a different orientation. That's what diffraction is. Now, there's also interactions between waves, not just a wave and a material, but wave and another wave. Let's say we have one wave looking like this, and it's propagating to the right. And then we have wave 2 that looks like this, and it's propagating to the left. Well, let's look at the point where the negative area or polarity of this first wave and the positive polarity of this second wave are overlapping. Well, that's what's actually happening. Both waves still exist. But what gets observed is that there's some positive area here, some negative area here, and then no visible or observable wave here between them. Where it looks like they cancel each other out, that's called destructive interference, or sometimes called deconstructive interference. But they haven't actually canceled each other out. We're just observing that effect of their overlapping differences in polarity. Now let's say wave 2 keeps moving to the left and wave 1 keeps moving to the right, such that both their positive polarities and negative polarities are perfectly overlapping. Well, that's going to cause constructive interference, where what gets observed is a wave with a substantially larger or higher amplitude on the positive polarity and a substantially lower amplitude for the negative polarity. So for that moment where they overlap, it looks even more intense. But then eventually wave 2 will keep going through, wave 1 will keep going through, and then they'll look like separate waves again. Now let's look at harmonic standing waves. In order to have a standing wave, you must have a material that the wave can travel through, and both points must be fixed so that each end point can't be moving up and down. Well, those points where the material looks like it's never moving as the wave is moving through it, that's called a node. And a harmonic wave has its harmonic number plus 1 number of nodes. Now, a harmonic standing wave will have the same number of antinodes as its harmonic number. And we'll represent the harmonic number of a wave as f sub n. F usually means the frequency, but in this case we're just saying f sub whatever number our harmonic number is. So the fundamental harmonic wave, or the first harmonic standing wave, f sub 1, that's where as our wave is moving through our material, it's making the material bend all the way up like this. And then as it reaches, the energy reaches the end here, it causes the material to bend all the way down like this. And the energy just keeps moving our string or our rope like this so that the rope is moving up and down. The points where the rope never moves, those are our 2 nodes. N plus 1 nodes, first harmonic wave, 1 plus 1 is 2 nodes. We have n number of antinodes, we will have one antinode. That's where we have a maximum change in amplitude as the material moves all the way up and then moves all the way down. For the second harmonic standing wave, or F2, our material is going to bow up for the first half and bow down for the second half as energy is moving in one direction. And as the energy of the wave reaches the end point here, it's going to make the material invert so that it now bows up here and bows down there. 2 plus 1 gives us 3 antinodes, here, here, and here. And then we have 3 number of nodes, and now we have 2, the harmonic number, 2 number of antinodes, where the material here is moving up and down with a maximum change in amplitude, and also moving here down and up with a maximum change in amplitude. As one more example, we have our third harmonic wave, F sub 3. Well, in order to draw this wave, we need to have 4 nodes and 3 antinodes. Well, 1, 2, 3, 4 nodes, and then 1, 2, 3 antinodes. The material will bow up, then down, then up, as energy is moving in one direction. Then as energy moves back, it makes material move the exact opposite direction. So now we have 3 antinodes where the material has a maximum change in amplitude of moving up and down, up and down, up and down. Whenever we have a point of our wave that's above our arbitrary axis, so it has positive area, that's called a crest. Whenever it's below or has negative area, that's called a valley. The physical distance between our axis and our point on our wave, that's called amplitude. Amplitude A is in units of meters. Lambda, the upside down looking y, is wavelength. That's also in meters, so it's a physical distance. That is the distance between 2 points on a wave that are at the same height and at the same point in the oscillation. So these 2 points here are at the same height, but they're not at the same oscillation. This is a point as the wave looks like it's going down. Here is a point as the wave is going up. But at the top of both crests, that's at the same point of our oscillation, where we have our 2 points here. From crest to crest, that is one entire wavelength, whatever that value equals. You also do a valley to a valley. Now, in reality, the wave doesn't go up and down, up and down. It's not doing this. It's actually just moving in a straight line. But parts of that wave are up here, parts of that wave are down here, up here. So as we detect it, we're detecting that change in height. But in reality, it's not doing this in one physical point. It just looks like that, but it's traveling like this. Now, F, if we're not using it to say the fundamental or the harmonic as a symbol, if we get a number for it in hertz or Hz, that's frequency. Hertz is just the same thing as 1/seconds. Capital T, or the period, is in units of seconds. K is the wave number. Omega, which looks like a W, is the angular velocity. And V is the speed of propagation, the speed moving in that straight line, because the energy is propagating in that straight line. Some relationships are that wavelength times frequency equals the speed of propagation. Lambda times F equals V. The period T, capital T, is just 1 over the frequency. In other words, period times frequency always equals 1. The wave number K equals 2 pi divided by lambda. the angular velocity omega equals 2 pi times the frequency. Now let's say that we have the following. For harmonic standing waves, the total length between our two endpoints is equal to the wavelength times the harmonic number divided by 2. Let's say we have a string that has a total length, capital L, of 6 meters, a speed of propagation v of 18 meters per second, and the mass of the string is 1 kilogram. Let's solve first for wavelength, frequency, period, and when necessary, for harmonic numbers n equals 1, 2, and 3. And then by the time that we're done, we'll solve for the tension force. Well, rearranging our equation, wavelength equals 2 times the length over the harmonic number, or L times 2 over n. Lambda 1, or the first harmonic number, the first harmonic wave, will be 6 meters, the length, times 2 over the harmonic number 1. That gets us 12 meters. For the second harmonic, lambda 2, that's 6 meters, times 2 over the harmonic number 2, giving us 6 meters for the wavelength. And for the third harmonic, lambda 3, that's the length 6 meters times 2 over the harmonic number 3, giving us 4 meters. For frequency, that equals the speed of propagation over the wavelength. So F1 is going to equal our speed of propagation, 18 meters per second, divided by our wavelength, 12 meters. That gets us 3/2 hertz, or 1.5 hertz. For the second harmonic's frequency, we have our speed of 18 meters per second divided by our wavelength of 6 meters, giving us 3 hertz. And then the third harmonic, that's the speed of 18 meters per second divided by our wavelength, our third wavelength, 4 meters, giving us 9/2 hertz, or 4.5 hertz. For the period just equals 1 over the frequency, and it will have the units of seconds. So period 1 for the first harmonic, that would be 1 over 3/2 hertz, or 2/3 seconds. For the second period, the period of the second harmonic wave that has these parameters, that would be 1 over 3 hertz, and 1 over a hertz is 1 over a second, or 1/3 seconds. And the third harmonic standing wave, under our current conditions, will have the period T3 equaling 1 over 9/2, or 2/9 seconds. Cool thing about tension force when it has a standing wave, a harmonic standing wave going through that material, the tension force F sub T equals the speed of propagation squared times the mass of the material divided by the total length from end to end that the wave is moving through the material. So in that case, no matter whether it's the first, second, or third harmonic, our tension force only depends on our speed of propagation, 18 meters per second, all of that squared, multiplied by the mass of the material, 1 kilogram, divided by the total length of the material, 6 meters. And a meter squared per second squared times a kilogram divided by a meter gives us kilograms, meters per second squared, or a newton. And our tension force for all 3 examples would happen to come out to be 54 newtons. Well, in any case, that concludes our bonus lesson for our discussion on waves and also looking at harmonic waves and the tension force when a harmonic wave moves through a material. As always, if you are not actually in one of my classes, you can consider leaving a comment, liking the video, or subscribing to the channel just to see that subscribe button turn a rainbow color. That's why I like to say it. If you are part of my actual class, well, hey, glad to have you in class. And, well, you can also do those things as well to this video. Whatever you do, thank you for being part of this and wish you all the best. And peace.